And thank you for coming to our next Value-Added Services workshop. This is going to be a technical workshop led by Jurrian, so I will give you the floor.
Thanks. Um, so what I had in mind, I hope everything is quite clear and the full screen will also work. Participant can see screen. This should work, I think. Drop this to the side somewhere. Mm, like this. Yeah. Thank you very much, everybody. I want to take the time today to discuss self-supervised learning and what to do with self-supervised learning and drones. How this has been implemented, and it's going to be a lot of deep learning talk as well. I want to do this as sort of a continuation from the previous workshop where we talked about like shortcomings in drone use, how to overcome some obstacles, some pitfalls, and then this one will be a bit more deeper into my own research at Wageningen, working with drone data, processing drone data, and how we get better generalizing models. I'll do a bit of introduction and will be a lot of talking from my side. Will be more of a lecture, but there's a lot of extra available stuff to get started with, which I want to emphasize to have more of a workshop feel. And I would definitely want to be able to be available if anyone wants to start with something like self-supervised learning. Um, I'll be here to help out, and I want to be very open for next emails for another chat down the line or something like that when people want to start with this subject. Um, yeah, so that's basically the main goal for today. Quick recap. The previous session we worked on the pitfalls, and I presented this four layer or these four steps. The flight step of the drone analytics, the data acquiring, data processing, usually happening through some kind of model, and then you end up with the information that says something about the subject you flew over. Um, and with all of these, there are specific pitfalls. So maybe there's too much wind, so you can't fly. So there goes your whole project already. Or maybe your information isn't well structured, or you took the wrong information instead of the end user want to report, and you ended up with a lot of data. Um, and we had discussions and breakout groups at the end discussing what kind of open call trial pitfalls there were. And I included these in the final blog post. Um, Today will be a lot more, very big deep dive into this middle bit, um, about the data and about the models and what kind of models to use and how to overcome some insufficient labeled data shortcomings. Um, why I care about it is part of the discussion. I have three examples of people using um, self-supervised learning methods. How I did it, so you can get started with a pre-trained model and just playing around with these models if you care. And then they finally getting started with this and some conclusions. I'm not sure how well I can see other people. I'm not too sure about that. But if there's anything, maybe Mackenzie can also say when there's something in the chat or something. Um, Before we begin, I see deep learning as Lego. This means that all these terms, all these fancy new learning methods, new architectures, transformers, everything is changing all the time. Now we have diffusion and generative AI. I see it very much like Legos. All of these blocks can sort of fit together. So there's different parts to a deep learning system. There is what kind of data you work with, of course, but also how you process this data. With drones, we really work with images, basically all of the time. And how I see it, it's a different kind of starting point. So our image gets processed by this model, and these models can be very adaptive, depending on the task you want, depending on what kind of thing you want to do. So maybe you have a top-down image of a field, and you want to select different plants in that field. You use different kind of architecture for that. And they can change around a bit. So maybe you want to have a ResNet 18 backbone, maybe you want a Vision Transformer backbone, what kind of task you want to do. It can also be anything. And what I often do is there's a lot of papers on what you can do, so I copy paste their code. You can craft sort of loss functions. So how does the model learn? What does it learn? And how do you fill all these parameters in this model? Um, Then you process your data set, so you make sure that your data set, your drone images fit what the model expects. And the hard bit is how to evaluate these. This is where the real science sort of comes in. What kind of test evaluation sets do you keep, etc. Very much deep learning is Legos. You can copy and paste many of these things to different, so you can have different backbones, you can have different heads, you can have different loss functions, you can have different data sets and different ways to evaluate, and they can all fit together in any way you really want. What I really focus on during my research is that there's many problems. We often see papers using deep learning and they work really well, but there's so many issues to overcome before we really get nice applications with deep learning and drones. It's that the datasets themselves are quite small and they're not complex. So what you have to have in mind is that your drone flies over the area, you get 500 images from the top or from the side, and that's really it. You really want to have information. In the end, you really want this drone to detect some sort of disease, for example. And using deep learning, this can be done, but you need, well, easily 10,000 images. And especially generalization then suffers because you have this smaller data set that's really focused on this one area of this one flight, of this one sensor, of this one flight height. You get very specific images. So you don't really train it to detect diseases in the plant, but you detect it to that disease on that plant, on that moment, on that data set. Um, yeah, so that's where the research that I really want to focus on and I tend to enjoy is maybe you can use deep learning too. Deep learning is now generative these days, so you can generate new samples. Maybe you have methods of not needing that much data, but still have a nice deep learning model. There's very many techniques to go over this, and the one we'll go over through today is the self-supervised learning and pre-training. So I'll go over some examples of how generalization suffers with drones. Which I keep mentioning. Let's say we fly a drone, we capture our data, and we want to see which plants are diseased. So we have our nice drone, we have a fancy sensor on it. We fly every week, and now we have a lot of data, just images and images and images and images. And then, wait, we need labels. Wait, we need to get our application going, but we need to see where these plants are. And that's usually manual labeling. So there's a person looking at the image, taking a taking some time to color in the correct image, the correct items in the image that say something about the disease. And after about 10,000 of these hard labor drawing, then you get a good model. You can put it into the model, all this training data, and then you get something out of it. This is a lot of human work. Many labels are needed. So perhaps what we need to do to get some nice applications going is we drop this need for labels. What if you only need like 5 or 10? And there's a lot of work going into this, like new models like Segment Anything work on this. So generalization, what I want to focus on is, for example, we have a data set which is really high resolution, but actually in our applications, we actually flew a bit higher and now our images are low resolution. There's some tricks you can do called multi-scale training, so you train on different zoom levels. However, you can already see if you are, for example, a model that wants to detect these lines, these power lines, well, they're not going to be visible on this. Your model collapses and nothing works, low accuracy. So you need more labels. What if we have a great model, but we trained it on multispectral images? Well, this is a very big domain shift. They go from this false color colored. So they go from these pink high infrared images to normal RGB image. Your model collapses. You need more labels or more training data. What if we have a composite RGB? This is very bluish and not really the bright green we know from a true RGB image. You need new labels. Now, some bigger ones. This is what I really focus on. What if you have this great data set of a vineyard? There's a nice orthomosaic on the left, the Bodegas de las Gaudas data set. And you have this great model to detect disease in this vineyard, but now you go to a different vineyard and it's completely different structure. So how do you translate? You need to restart almost by labeling the new vineyard because this step between this vineyard to the left with all this green rows in between, there's a lot of grass, is of course highly overfitted on this Bodega's the dataset and not on the CAN dataset. Another problem we often see with drones, you have a lot of data that's captured from nadir, from the top to looking down. And then maybe when you have a new data set, you acquired it from a bit of an angle, and then you start all over again. These images are very different and the model will collapse. Need more labels. So there's a lot of generalization issues which deep learning can solve if you have enough data. And with enough data, I mean enough labeled data. A lot of human effort goes into that. So this generalization issue is that there's a lot of variance when flying drones. There's different flight heights, there's different sensors, there's different topics you can fly, or different applications you can build. There's different uh, sun, or even like sun angles are different, and then the model collapses again. You just need so much labeled data. Um, This is also where the typical overfit curves come in. So we have our amazing model. So this is sort of what happens during training. It optimizes and optimizes, it gets better. And actually here, wow, you have a great model. And during continued training and your data set really takes over and it gets really good, like 90% accuracy, 95% accuracy. Um, on low training error on your training data set on the top-down images, for example. But then you do a new application and your angle is now changed and you get your test data set going, so a different data set, and then you see that the accuracy goes down again, so the error goes up. And your model is actually not that great when it's here. Even here, it's not great, but we want, of course, our applications need to be so accurate. When you want to count sheep, you need like 99% at least accuracy. Otherwise, you're going to miscount sheep, and then, well, there goes your application. So we need to be in this bottom right, but then also on all these different variances we can imagine. So that's a lot of data still needed, labeled data. Yeah. So what happens in the outside world is usually your test error goes up crazy. This is where self-supervised learning then comes in. I want to start off with self-supervised learning is not the only answer. There's so much going on in this field of generalization. There are so many different tricks. There's so many different tools you can use. You have things like domain adaptation and style transfer. So you see people that can change, for example, the daylight when you have a data set on daylight A, when the sun is at this angle, and then you want to apply it on when the sun is at this angle. There's like domain adaptation, style transfer tricks you can do. Also like test time adaptation, that there's a different kind of model to use. Semi-supervised, so you only need like 5 labels and it will try to do the rest itself. What we often see, and you also saw it in discussion with the open call trials, you tend to use an underfitting model. So these are sort of more general, like a random forest. These are not complex like a deep learning model. They are a bit more explainable, so you can say what's happening under the hood. And they tend to be good, but not great. They tend to hit 60, 70, maybe 80% accuracies. The deep learning really showed that you can get to 95 or 99. So this is where sort of the research comes into. Um, Ideally, we have a great deep learning model for drones that can do all these different tasks at great accuracies without needing to change because the different sensor angles, it can deal with it. It can deal with all these differently domain shifts I just gone over, different sensors, different utilities, different tasks. Um, but we will never, I think, much my personal opinion then, we will never get to this amount of data. We will never get enough labeled imagery. We need probably millions of images and labels to get there, especially labels. And I don't think we're going to get there anytime soon. So we need different applications, which comes to my topic right now of self-supervised learning. The popularity gained mainly with the GPT era, so the generative pre-trained text models, the large language models. They just throw a lot of text at it. No actual task. They don't say, hey, try to summarize, make a summarization task. There's no task. There's just predict the next text item. And then they do a few tricks. And then they can create a large language model, which is actually quite a nice chatbot. So self-supervised learning tries to give this model, any model, like a transformer model or an image model or a generative model, you want to give it a task that you only need your input data for. There's only our drone flights. We only take all the images from the drone flights, no labels, no text, no anything, just the images. And then we try to make it learn something from that data. This is this pre-text task. You give so much data that, well, it always needs more. And now it can actually do this pre-text task. But that what they figured out is that if you have this GPT model and you just give it all this, like basically half of the internet to read on, it will learn how to read, which is actually quite useful. So we can also do it for images. So it will understand the general structure of an image and of course the general topics inside of an image. So it can generalize quite well. For images, it's all about augmentation. So you want to shift it, you want to zoom, you want to shift the colors a bit, you want to zoom in, zoom out, crop, turn, rotate. Your loss is often about reconstructing these different augmentations of trying to maximize the variance between these images and minimize the variance for the same image. Sadly, the batch size, so this is the amount of images a model sees at the same time, needs to be huge. A normal computer will be able to do like 8 or 16. You need over 200 images per batch at least. This means massive computers, server sides with huge GPU capabilities. This is the downfall, or the not the downfall, but the difficulty with self-supervised learning. It needs a lot of compute. And then in the end, you don't get a ready model. So after they've seen all these models, you get a model that understands your data set a bit. Then that means if it already understands it through this pre-text task, you need probably less labels. That's the main goal. And you can plug and play a bit with different backbones to train, different heads, different tasks to different pre-text tasks to figure out. And this is sort of the whole field of self-supervised learning, where hey, we have a new paper, we have one new trick to figure out how to do this learning, or hey, we have a new backbone introduced, or a new task. And that's where all these new papers come in, all these nice deep learning papers. So for example, take SimCLR. They have this input image. This GIF is from the GitHub repository that they made themselves. So for example, you have your input image of a dog, and then they make two versions of it, two augmentations, one more of a zoomed in crop on the head of the dog, one on the backside of the dog, and then they also shift a bit the colors around. They pass it towards this deep learning network, a convolutional neural network, which learns some sort of representation. And then between different subjects, so a chair and a dog, they learn to maximize the variance between these samples, between these basically rows of numbers. And between the samples, they want to attract as much as possible. Interestingly, they figured out you have this large data set called ImageNet, and without needing anything to say that this is a dog, it will understand dog images as being similar. So dog images are clustered very close together. Chair images are very close together. And this is all it has done. It doesn't explicitly say it is a dog or it is a chair. It only knows these different images are more dog-like, these are more chair-like. That's what SimCLR does. So this is contrastive learning. There's Siamese learning, where you have the same models that also learn on different augmentations. And the trick with Siamese learning is that not the whole model gets the weight updates, like this one, but only the prediction branch gets updates and not all the target branches. So you get 4, in this example, a prediction branch and then 3 views, usually. You take the mean output of these views and you make these as similar as possible. So the top one sees the original image, the other 3 see the copied, augmented image, and you make these different augments as you take the output of this model is some sort of random number basically, and you want to have this number as similar of this model than to these models, and then you update this final model and there's like a stop gradient. Doesn't matter that much. What they figured out, they can do it on a single GPU. In practice, it doesn't really work that well, or especially not compared to contrastive learning. I worked with this a little bit. I also emphasize these. These work by heavy augmenting of the input image. So these rows are the same image, but this one is the original, and these are very zoomed in, very contrastive, more contrast added, more a bit of HSV shift, so there's a bit more light, a bit less light. And the same counts for this row. These are sort of examples of how the augment looks like. Also gets around 75% on ImageNet. ImageNet is quite an easy task these days. It's quite old. It's like 15 years or something. So it's quite easy to solve with self-supervised learning. I applied this on drone images. I took different kinds of drone data. So a lot of 4-channel multispectral, so blue, red edge, and NIR images. I trained on a batch size of 16 for around 10,000 steps. So it sees around 160,000 images in total. The total data set was around 100,000. I explored different backbone architectures and how this works. There's a paper on it and also a nice GitHub to start with. It's not as great for different dense tasks. So what I mean with that, with dense tasks, is that you have the input image and you also want to see the complete subject of it. Um, so your input image has all these different kind of plants, and you want this plant level detail. It can also, what FastCM does really well is that says something in general about the image. So this image contains a boat, is what it will say, for example. Or this image will contain a ship. But with dense stats, you can say this is where the ship in the image is, which is of course way more interesting for drone analytics. You want to see where things are. That's the whole point. So dense task is not too great for FastCM. It's a learning curve, so it learns very quickly to take the minimum variety. In around 4,000 learning steps, has already learned most of the variance in your dataset. It's very quick, but also not that great, sadly. Then we have the big one. This is what everybody uses these days. Mask image modeling. You take your input image, so this normal image, you make most of it black, usually in around patches, so around small blocks of like 16 by 16 pixels. And you try to reconstruct this image from just this input. And then over time, it will learn how to do that. And in the meantime, this whole backbone, so part of the network, will see some sort of generic features. It will understand what your images looks like. There's so many architectures to do this. This is also where the Lego thing comes in again. Everybody has figured out a way to do this on a different way. How do you do this input? Masking is different. How you construct your model is different. How you do the reconstruction is different. However, one general thing is this narrow bit of the network. So the deep learning network is often very broad in the beginning, sees not that much information, and it goes very narrow, has a lot of dense information, and it contracts again. This very narrow bit needs to be very narrow, like a very high compression rate. This will make the model learn as much as possible. So no skip connections, like different deep learning tricks. Yeah, there's many papers on it, but this is generally mass image modeling. Very nice. It's a lot better than the other ones. Works on dense tasks. Gets even higher accuracy. This is also, of course, what the whole transformers hype has been about. What we see a lot of geo AI foundation models is basically this. They take all of the satellite images in the world. They say, hey, this satellite image is from a radar system. This one is from a normal camera. This is the GPS location. And you sort of mask out the images. You mask out this extra information it tries to predict. So maybe it only sees radar images and needs to predict what the RGB images looks like. This is the whole pre-training step. This is the whole foundation is basically mask image modeling. The trick what they figured out with the whole satellite world is kind of nice. They have huge amount of data sets which are all open source. They have the Landsat 8 has been around for 30 years. It's been gathering around data for 30 years. Every week, the image is seen again, the area. So there's so much data to train on. And that's where these geo embeddings, all this stuff is just mask image modeling of a fancy model. And like I said earlier, there's different methods to mask your image. Maybe you do like a random pattern, maybe you do patch, maybe you do token level, feature level, where in the model you mask it out. Usually this patching, this small blocks of 16 or 32 by 32 is usually best. The variance between accuracies is not that different, like 80.1, 80.2 accuracy, etc. So here's some geo AI foundation models like Copernicus. What you see is masking right there. And what you see also with Galileo, another model, masking, masking. Everybody just, it's a big transformer and there's masking. And that's how they learn all these embeddings, these time changes. Everything can be learned through masking. This then needs to be translated to drones, I thought. What if we can also do this? Because then we can learn something about our data set without needing all these labels, because we don't just do masking. What kind of input do we often work with? What kind of output? Which tasks should we focus on? So I thought maybe I'll just start with a simple model, get a decent small backbone, make sure that all the code is open, all the code is online, um, present some sort of downstream tasks that we can work on, like maybe we want to detect berries in a field, maybe we want to segment out items or typical drone related items, and start with a simple two-stage design. So an encoder part, which is trained and pre-trained, but in pre-training in this mask image modeling method, and a decoder, which is tuned on the specific data set. Um, so I came up with classical European project, a nice Greek title. Um, it's a pre-trained aerial self-supervised integration of paired and hybrid data. So I work with RGB data and I work with multispectral data at the same time. That's what I'm gonna talk about in the next few minutes. Um, what this model looks like, how the model has been trained, and how it works or how well it works on different downstream tasks, and also compared to some other model. My model works with RGB and multispectral 5-channel multispectral images, either or. So you can do either RGB or maybe you want to do both. Maybe you want to do one of them. It's basically a conv-next model. These are basically state-of-the-art backbones. They are faster than all the transformers around, but they are slightly better than all the transformers around, so they're a bit better. They also go quite small and narrow and easy to run on a smaller computer system instead of the massive transformers that get billions of parameters. These have, yeah, just like a tenth of it, and it works really well. Here's the block, the design. How I trained it, I did two different types of training. First, some masked image modeling. Just like I said, you mask out part of the image, like a multispectral image, and it tries to reconstruct this image again. And then this is through a level 1 loss. So you basically directly compare what this image looks like versus what the original image looks like, and that's your error. Then what I also did, some nice tricks you can do, because there's these different pathways the data takes. There's this multispectral input, it goes through the model, and it reconstructs at the output. But then what you can actually learn, if the images are from the same location, from the same sensor, basically, like we often see these days, is that you take your RGB input and you try to reconstruct the multispectral input. You take the multispectral input and you try to reconstruct the RGB input. And you use the same heads that are already been trained on masked image modeling as well. This means that all the RGB information, all the multispectral information needs to be processed like through each other. These are direct examples from the training. This is how well the model works. So it predicts quite, not very highly detailed, but nice information nonetheless. This is a tree from the top. There's no label saying this is a tree. It just learns how to reconstruct itself as a multispectral image or when it's masked out as an RGB image. This will make sure that the backbone learns all the different multispectral items, what they compare in RGB space, in multispectral space. And we get a nice model that learned how to do this. This is the decoder side. It's a VQ GAN decoder. Doesn't matter. This is all done. This is not that interesting. Then our data set. So over the past few years, we have all these different ICAERUS projects, all the use cases, different data sets that have been included through the open call trials, me searching online what kind of data sets are out there using drones. And I developed this huge data set. Well, for us, it's quite big. It's 500,000 images. And they're pre-processed in a very similar way, especially if they're from the same location, to make sure that they're aligned and that they're at 512 by 512 chips for these smaller images. And then we save them. And this is, of course, a pre-training data set. It's all these images of vineyards, of forests, of the different open call trials, of different use cases, of the different things. So everything has been online and open sourced. I included it, and also a lot of online contributions that I just looked around on Zenoda and on Data and Brief, resulting in like 500,000 images to pre-train my model on. I trained it on a batch size of 265 at the same time, trained for around 1,500 steps, so it's seen around 400,000 samples. So it hasn't even seen the full data set. But this is also where the loss sort of stopped working well. This is the loss over time. You can see it's quite going up and down a lot. This is partially because of batch size, because of training duration. You can train endlessly long, but at some point it will sort of hit um, this straight line. So it started off learning a lot at the beginning, and then over time it goes down and down and down and down, and then it sort of flatlines at the end. I think you can train for another week or something, but then it doesn't really make that much of a difference. It has seen most of the images. There's not that much variance in our images. There's a lot of vineyard images which look very similar. So I thought, wait, I'll trained long enough. I'll stop it here. This is what the training process looks like. So these are the first few steps. Tries to figure out what the structure looks like, and then start to get slightly more detailed as time goes on, but not perfect, and that's fine. We don't want a perfect reconstruction. We want a great reconstruction, very highly semantically clear. Also, this one, RGB to RGB. So it learns finer and finer detail, and at some point it sort of just stops. This is all it can learn for that point. And I thought, this is a good moment to stop. Especially in this one, you can see quite clearly it started off a bit of a mess. And then over time, you can see these different lighting and plant and leaf conditions in this tree slowly take shape. And near the end of training, it's quite accurate. And of course, I work with all the open call trials. I make sure that use cases upload all their models, their data. So I do the same. This is all the whole model weights, all the code, all the training, all the notebooks, how to tune your own model, how to adapt my model. It's all on GitHub, as well as the data set. There's a whole attached paper to it, how we pre-processed it. It's all online. I think this is the only way to properly do this, and also a nice way to give back again. Now to evaluation. So we have our model. It's going to be great. It's completely pre-trained, but now we need to see how good is it. We want to do as many benchmarks as possible. We want to compare it as many other models as possible. We want to make it as hard as possible. So what I found 4 relevant data sets, which are kind of I found online. These are not seen during training at all. I kept them separate. And I compared to a Dino model. This is the newest Facebook Meta AI model, which is trained on 1.7 billion images for like multiple weeks. So a lot bigger of a data set, a lot broader of a data set, but we're going to use it to compare against. So it's a lot better of a model probably. And we want to make it as hard as possible. So we want to reduce the amount of labels needed to get a nice task going. So how I tested this is that I only gave it one sample. So when you want to detect berries, I only give it one berry per class. Maybe there's 4 different types of berries. I give it 4 images. Done. For the one shot. And for 10, I give it 40. This is really difficult for deep learning. This is not what it's good at. And this is what we need for actual applications. We need to only give like, here's some labels, here's some berries. Now do the whole data set. This is the starting point. So this is the detection model. It's an FCOS detection model. It's all implemented. You don't need to care about it too much. So I trained it on these few images, and what you can see is that my model can actually detect after only seeing 10 images, 10 samples of this berry. It can detect it, the same as the Dino model, but they see 2. This is a very difficult data set. I almost can't see these berries. And there's one there, and there's one there. The model's okay, but not great, especially this class with very dark berries. Very difficult to detect. Dino gets quite close, but not perfect either. Some more examples of this bottom image. Sadly, this means we're not there yet. Self-supervised learning can only get us so far. It does some of the classes, so this quite obvious berry and also the very orange berry does quite well, but we're not quite there yet. This, of course, in your mind for different tasks, this can be translated to anything. You can use the same backbone. You can use my architecture and you can tune it on your own task. Maybe you want to see cows, maybe you want to detect sheep, maybe you want to detect the disease in plants. Anything, it can be tuned. it can be applied. This is the berries example. Um, the more labels you have, the better it will do, sadly, still. There's not really like it will just keep going better and better. Maybe after like 1,000 labels, you will sort of hit the ceiling, but 1,000 labels is still a lot, especially in drone images. That's a lot of hard labor needed. There's a weeds galore dataset, which is basically a top-down images of weeds in a field, and there's different types of weeds. There's like 6 or 7 different types of weeds, all nicely drawn out. This is all manual labeling. This is all done by hand. And you can see that especially only giving it 1 sample per class and giving it 10 samples per class makes a huge difference in the results. The left one is my model and the right one is the dyno model. They're about the same, I'd say. I could give you all the specific accuracy details, but it's a bit boring to go over the exact numbers. Turns out they're sort of side by side. My model tends to be quite, or not slightly, just a bit better than the big 1.7 billion training images dyno model, but comparative. Um, Another task, you can convert RGB to NDVI images. And this is the ground truth. This is the pure actual NDVI images. This is the RGB images. And of course, then you don't need a multispectral sensor anymore if you can do this. My model only seeing 10 samples did quite well, I'd say. And the dyno model really doesn't do well. It tries to underemphasize, overemphasize massively. On this image, it does a bit better, but on these, it's not that great at all. I think this is because my model is much more used to this top-down RGB images of vineyards and of different locations than the dyno model is, which makes my model a bit better. A lot of talking, a lot of examples, a lot of deep learning chat. I just want to say that you can use this model right now. If you have a task in mind, if you want to detect something, see something using deep learning, this model is the first half of your model. All the code is there, so you can just say something about, hey, this is what the dataset should look like. This is what the uh, different labels look like, and you can train it, you can run it. All the codes and things are up there. This tuning part, so what I expect all the different tasks to do, doesn't need that big of a GPU. My laptop works as well. My model is great. Dyno V3 is also great. The older Dyno models aren't good enough, especially on higher resolution imagery. They don't work well. So when you have flown your data set, what I think will work really nicely, what we'll probably will see also happening in the coming years, is you have your data set of maybe you've flown for 6 months, you've flown every week, you have all these images, and now you want to do something with it. You can actually use this whole mask image modeling, this pre-training, my model, dyno model as a starting point. And then you sort of just do mask image modeling on your own specific data set of all these images. So it knows a bit the variance between the images, between the subjects within your image. Maybe you have a lot of plant images and tries to really focus in on uh, different types of grapes that will be within the image. So what I expect the coming years to happen is we'll see a lot more mask image modeling first step, and then tuning on the exact maybe disease detection task of the grape detection task, but always starting with mask image modeling. And before that, you can still start with my model, the Passify model, then also still do mask image modeling and then do the tuning, or just do my model and then directly to tuning. They will be quite similar. In summary, deep learning is really like Legos. You can copy, paste, adjust. There's some, of course, Python, PyTorch knowledge needed. And I think, and what the results show is that it can partially overcome label shortage. So it needs a lot less labels to get a good result, but not perfect. So we need a lot more data still, and we need to figure out how to do this pre-training and maybe even slightly towards tuning on these different tasks already. Um, all of this is available. You can start with it, and I can help out in any way with using this model for your different tasks you have in mind. And they will work well, but you will still need labeled data. We're not there yet. We cannot. There's really nice documentation online to get started with this. On self-supervised learning, there's this whole library called Lightly. It's really nice to work with, focused on images. My model is online, especially my notebook section. And there's also a full research article about this coming out soon. Before going to the question and answer, I thought maybe I'd open this and showcase a bit. Doo-doo-doo. Basically a summary of the chat I just gave. There's this notebook section, and you can do detection. So what this detection notebook looks like is, hey, I want to do a detection of an item. This is bounding boxes. Like I want to detect where the objects in my images are. The dataset is, or the modules, so this is what you need to do yourself. If your dataset looks a bit different, you need to figure out how to do this. However, my model expects an image with these different images in there, and of course, different targets. So the labels. So this is where the images or the objects within the image are. This is an image of a cow in a field, but I just want to see where the cow is, so I give it just a smaller target. I say how to format it. Wild bee is, for example, the berry dataset. It's the boxes, so I gave it a few samples. So it's loaded here. You see everything. You load the model, so it basically load from checkpoint. This is my pre-trained checkpoint, which you can download. You attach this detection section on it. So this is just copy paste, copy paste, copy paste. I want to log some information on weights and biases, and then you train. That's it. That's all you really need. So most of the work will be in this creating this data set, this data module. We see different section of the model. You can see my backbone is 2.7 million parameters, not even close to large models, and only the detection head is like 10 million models. This is kept frozen because we want to remain our pre-trained items, and this will be trained. And the loss will slowly go down over time, as you can see here, and it will learn as much as possible from the training data. And then, of course, this is some help functions, you can just ignore it completely. And we want to test it. So we run all the code. We have our test data set, which is not seen during training. And then you can see the accuracy right there as well. And some visualization, because it's always nice to visualize what you've been up to. Something similar for the segmentation, and I think what we often see people really focusing on is that these features are very nice. Oh, I closed it. Yeah. So feature visualizations are also quite normal to showcase. Also one example of that. That's a lot of me talking. Maybe there is some questions. If not, then I'm happy to end it there as well. Thanks so much for listening, everybody. That self-supervised learning was probably quite a lot, quite quickly. Sorry for that, but there's just a lot of information to get started with. So that's why I did that. Thank you.
Well, if there's no questions, if anything comes up, you can always get in touch with Jurrian. But thank you very much. And for those of you that joined, we'll be in touch again for the next workshop, which will be for sure on the triple layer canvas. And we're looking into another one on life cycle impact assessment. So thank you very much. Have a great day.
Thank you.